Hello and welcome, dear listeners. I am Dr. Geraldina Fernandez, Associate Professor in the Department of Mathematics and Statistics from the BHOPAL School of Social Sciences. Dear learners, in the last few modules, we have discussed about linear differential equations and methods that are used to solve linear differential equations. So now, in this module, we are going to discuss about those equations which are reducible to linear equations, that is Bernoulli's differential equation. So, before moving further, let's first discuss the topics that we will cover in this module. So, in this module, first we will discuss the definition of Bernoulli's differential equation. Second, we will discuss the working rule or the method to solve Bernoulli's differential equation. And at the last, we will practice few questions. So, a differential equation of the form dy by dx plus py is equal to q into y raised to the power n, where p and q are constants or functions of x only, and n here is a constant other than 0 and 1. So, this type of equation or differential equation is called as Bernoulli's differential equation, and it is also the standard form of Bernoulli's differential equation. So, this is Bernoulli differential equation in y, since here the dependent variable is y. Similarly, we have another Bernoulli differential equation in x, that is given by dx by dy plus p dash x is equal to q into x raised to the power n. So, this is Bernoulli differential equation in x, where x is the dependent variable, and the first one is Bernoulli differential equation in y, because here y is the dependent variable. So, here if we talk about the p and q, they are either constants or functions of x, whereas n over here has three cases. Now, if you take n is equal to 0 in this equation number 1, it becomes linear differential equation that we have already discussed in the previous module. That is, it becomes dy over dx plus py is equal to q. So, this is the standard representation of linear differential equation in y. Now, here first case was when n is equal to 0, we get linear differential equation. Then the second case is when n is equals to 1. So, in this equation 1, when n becomes 1, this transforms into variable separable method. So, we can solve this by variable separable method. Now, our concentration is when n is not equal to 1. So, when n is not equal to 1, it becomes equation that can be reduced to linear form and is called as Bernoulli differential equation. So, let us start with the working rule or the method that is used to solve Bernoulli differential equation. So, the Bernoulli differential equation is given by dy by dx plus py is equal to q into y raised to the power n. Here we have three cases for n. When n is 0, the differential equation number 1, we can mark this as equation 1, becomes linear differential equation. When n is equals to 1, it becomes the equation can be solved by variable separable method that we have already discussed in the previous modules. Now, our main concentration is on the value of n when n is not equal to 1, that means it is not 1, it can be any other value. So, then the equation becomes Bernoulli differential equation. So, now the question is how to solve such type of equations. So, step number 1 is we eliminate the term y from the right hand side. So, this can be done by dividing equation number 1 with respect by y, dividing equation 1 by the term that is appearing in the right hand side, that is y raised to the power n. So, we will divide the whole equation by y raised to the power n, and we will get 1 by y raised to the power n into dy by dx plus p into y divided by y raised to the power n is equal to q. So, here we can take y raised to the power n in the numerator, and we will have y raised to the power minus n into dy by dx plus By power and exponent property, we can solve this. Power and exponent property, we can solve this. We will get P into y raised to the power 1 minus n is equal to q. So, this is the equation number 2. Now, this was the first step, that we have to eliminate the term that is appearing in the right hand side, that is consisting of y. So, we divide the whole equation by y raised to the power n. Now, step number 2 is we use substitution method. We substitute y raised to the power 1 minus n is equal to v and mark this as equation number 3. From equation number 2, we substitute y raised to the power 1 minus n as v. And then step number 3 is we differentiate equation number 3 with respect to x on both the sides. So, in the next step, we will differentiate y raised to the power 1 minus n is equal to v, y raised to the power 1 minus n is equal to v. This is equation number, I suppose this is equation number 3, and we differentiate it with respect to x on both sides. So, we are differentiating equation 3 with respect to x on both sides. So, what we will get? We will get 1 minus n y raised to the power 1 minus n plus 1 dy over dx is equal to dv over dx. So, what formula are we using here for the left hand side? We are using the formula of d by dx x raised to the power n, that is nx n minus 1. Here we are using this formula. So, here y is a function of x, so we will have to use chain rule that we have already discussed in the previous modules. So, nx n minus 1, so here this becomes minus 1 and plus 1 will get cancelled. So, we will have 1 minus n y raised to the power minus n dy by dx is equal to dv. We can mark this as equation number 4. Now, what we will do, we will substitute the value of equation 3 and 4 in equation number 2. So, we will substitute the value of equation 3 and equation 4 in equation number 2, so that it transforms into a linear form of differential equation. So, this was our equation number, number 2. We can replace this whole term with another dependent variable, that is v, and this y raised to the power 1 minus n can also be transformed with v, and we will write the new equation as, so here the new equation, or you can also write it as y raised to the power minus n dy over dx is equal to 1 divided by 1 minus n into dv by dx. So, rather than substituting this, we can substitute equation 4, we can mark this as equation 4 and substitute the value of 3 and 4 in equation 2. So, what we will get? We will get 1 upon 1 minus n dv over dx plus p v is equal to q. So, on the next step, what we can do? We can take the LCM and we will get dv by dx plus p v into 1 minus n is equal to q into 1 minus n. So, we can mark this as equation number 5. Now, we can see that from equation 1 to equation 5, we have transformed a non-linear differential equation into a linear differential equation in V. So, this is a linear differential equation in V. Why? Because here V is the dependent variable. So, from equation 1, which was a non-linear differential equation, we have transformed, we have used some substitutions, and then we have transformed it into a linear differential equation. Why this is called as a linear differential equation? Because here the dependent variable y and its derivatives, they are appearing in the order 1, as well as the degree of these derivatives is also 1. So, here you can see that the dependent variable is v, and the degree of v as well as the power of this derivative is also 1. So, this is a linear differential equation in V. Now, from this on we can solve it by the usual method, that is we can find the integrating factor and then we can find the general solution of the differential equation in the form of V and x. So, now let us start with solving some questions. So, let us understand this concept with the help of few examples. Question number 1, solve dy by dx plus y by x is equal to y square. So firstly, we will have to check that the given differential equation is either linear differential equation or Bernoulli differential equation. So for that, we will have to check first what is the dependent variable. So here y is the dependent variable. So next step is we will check the degree of y and its derivatives. So here the degree of y, the derivative is 1. The degree of this derivative is the whole power of the derivative, that is 1. The degree of y here is also 1, but the degree of y here is not 1, it is more than 1. So therefore, this differential equation cannot be linear, because by the definition the term linear means it should have 1 degree. So here this differential equation represents Bernoulli differential equation. Why? Because the degree of the dependent variables and its derivatives is not 1. So this is Bernoulli differential equation. Now to solve this type of equation, first we will eliminate the term of y from the right hand side. So first step is we can mark this as equation number 1. So we will start with the solution. We will write the given equation. The given equation is dy by dx plus y by x is equal to y square. This is our equation number 1. Now since we have understood that this is a Bernoulli differential equation because the dependent variable here are not in degree 1. So we will eliminate y from the right hand side, that is we will divide equation 1 by the term that is appearing in the RHS, that is y square. So this will become 1 upon y square dy over dx plus y by x will remain as it is. We will divide it by 1 upon y square is equal to 1. So next step is we can shift this to the numerator and we will get y raised to the power minus 2 dy over dx plus we will cancel it out, we will get 1 by x into 1 by y is equal to 1. So we can mark this as equation number 2. So this is the very first step, we have divided the equation 1 by y square. Now the second step is you have to use substitution method. So what you have to substitute? You have to substitute 1 upon y with v. So we can put 1 upon y is equal to v. We can also mark this as equation number 3. So this is the second step. Now after this we will differentiate equation 3 on both sides with respect to x. So now we will differentiate it. So differentiation of 1 upon y will become minus 1 by y square dy over dx. Why? Because y is a function of x, that is equal to dv by dx. This is equation number 4. Now as we have already discussed the method, we will substitute the value of equation 3 and equation 4 in equation number 2. So one more step we can do here. We can multiply this whole equation, the last equation, by minus sign. So or we can write it as y raised to the power minus 2 dy by dx is equal to minus dv by dx. So this we can mark as equation number 4. So the third step is to substitute the value of equation 3 and 4 in equation 2. So you can now clearly see that in equation number 2 you can replace this whole term with equation number 4. See, this whole term can be replaced from equation 4 and 1 upon y can be replaced from equation number 3. So you can replace it from equation 4 and here you can replace it with equation number 3. So therefore the equation transforms to, we will get minus dv by dx, this is the first term, and then we have plus 1 by x into 1 upon y, and 1 upon y is nothing but v, is equal to the right hand side of the equation is 1. So now we can simplify it, we can multiply the whole equation by minus sign, so or we will get dv by dx is minus of v upon x is equal to minus 1. So this we can mark as equation number 5. Now you can have a look at equation number 1 and equation 5. Equation 1 is Bernoulli's differential equation, and with the help of these substitutions you have transformed Bernoulli differential equation, which is a non-linear differential equation, into a linear differential equation in v. Why? Because the dependent variable over here is v and the degree of v and its derivatives, they are all in 1 degree. So therefore, this is a linear differential equation. So we can also check it once again. Here equation number 1 was Bernoulli because the dependent variable was y. Here the degree of y and its derivatives was not 1. So we used this substitution. We have used this substitution and transformed equation number 1 to equation number 5, which has now become a linear differential equation. So now this equation number 5 can be solved by the usual method of linear differential equations. That means first we will have to find the integrating factor. So IF is equal to, here we can also write the value of P and Q. So what you can do, you can compare it with the standard equation, that is dy by dx plus P dash y is equal to Q dash. This is the standard linear differential equation. You can compare and get the value of P dash and Q dash. So here P dash is how much? P dash is the coefficient of y. Here y can be replaced with v. So coefficient of v over here is minus 1 upon x, and Q dash is nothing but the right hand side of equation number 5, that is minus 1. So next step is to write the formula for integrating factor, that is given by E integral P dash dx. Substitute the value of P dash, so that is E integral minus 1 upon x dx. So integration of 1 upon x is log x, so E raised to the power minus of log x. By the property of log, n log m can be written as log m raised to the power n. So we are using the similar property over here, and this will become, IF will become e raised to the power log x raised to the power minus 1, which is x raised to the power minus 1, and that is nothing but 1 by x. So the integrating factor is 1 by x. Now we will find the general solution of equation number 5. So the general solution is given by the formula v into integrating factor is equal to q is equal to whole integration of q into integrating factor dx plus c. Here c is the constant of integration. So what we will do, we will substitute the value of the integrating factor and q. So here integrating factor is 1 by x and the value of q was minus 1 multiplied by 1 by x dx plus c. So v by x is equal to integration of 1 upon x dx plus c, or v by x is equal to integration of 1 upon x is log x plus c. So last step is to replace the value of v that we have already written in equation number 3, that is v will be replaced with 1 upon y. So this is the last step. So we will replace 1 upon y into 1 upon x. We will replace the value of v as 1 upon y multiplied by 1 by x is equal to minus of log x plus c. So or the final value of 1 upon is 1 upon y is equal to minus of x log x plus cx. We have multiplied this x to the right hand side. So this is the final solution of the Bernoulli differential equation. So now the second question is, you have to solve x dy by dx plus y is equal to y square log x. Now here first you will have to check whether the given differential equation can be solved by linear differential equation method or by Bernoulli's differential equation method. So for that you will have to check the dependent variable. So in this differential equation, the dependent variable is y. So first we will check the degree, or you can say the power of y and its derivatives. If they appear in degree 1, then we can say that we will solve it by linear differential equation, or else we will solve it by Bernoulli differential equation. So here you can see that the degree of dy by dx is 1, the degree of y is 1, but here the degree of y is not 1. So this equation is Bernoulli differential equation. Now how to solve this Bernoulli differential equation? So we will begin with, we will write the given differential equation x dy by dx plus py is equal to plus y is equal to log x multiplied by y square. So here first you have to compare it with the standard form of Bernoulli differential equation, that is dy by dx plus py is equal to q into y raised to the power n. So this is the standard form of Bernoulli differential equation. That means the coefficient of dy by dx should be 1. Here the coefficient of dy by dx should be 1. But here in this particular question you can see that the coefficient of dy by dx is not 1. So first step is to divide the whole equation by x, so that it transforms into the standard form of Bernoulli differential equation. So we will divide equation, we can mark this as equation 1 and divide equation 1 by x. So this becomes x divided by x into dy by dx plus y by x is equal to y square into log x divided by x. So this x gets cancelled and we have dy by dx plus y by x is equal to y square into log x by x. So we can again mark this as equation number 2. Now you will have to check with the term that is appearing in the right hand side. We have to eliminate y square from the right hand side. So what we can do? We can divide the whole equation by y square. So next step is we will divide equation 2 by y square on both sides. So here we will get 1 upon y square into dy by dx plus, for the second term we were having y upon x. So y upon x was already there, we are dividing it by 1 upon y square is equal to y square divided by y square into log x divided by x. So in this step we will cancel it, we will cancel out the terms, this whole will be cancelled and we will have y raised to the power minus 2 dy by dx plus 1 upon x into 1 upon y is equal to log x by x. So this was the very first step after dividing the whole equation by x, after transforming it into the standard form of Bernoulli differential equation, we have to remove the term of y from the RHS. So we have done that. Now the second, we can mark this as equation number 3. Now the second step is, from this particular equation we have to substitute the value of 1 upon y. So what we will do? We will put 1 upon y as v. Mark this as equation number 4. Now the next step is to differentiate equation number 4 with respect to x on both sides. So what we will get? We will get minus y raised to the power minus 2 dy over dx is equal to dv over dx. Or you can multiply negative sign by the whole equation and we will get y raised to the power minus 2 dy over dx is equal to minus dv over dx. So here we can mark this as equation number 5. So next step is to substitute the value of 4 and 5 in equation number 3. So here only you can see that the first term can be replaced, the first term this can be replaced from equation number 5 and the second term 1 upon y can be replaced from equation number 4. So here we will substitute the value of these equations 4 and 5 in equation number 3. So what we will get? We will get minus of dv by dx plus 1 upon x remains as it is, 1 upon y can be replaced with v is equal to log x by x. Now here we are having a negative sign, so we can multiply the whole equation by negative sign, we will get or dv by dx minus v by x is equal to minus log x upon x. So now this is equation number 6. Now you can go back to equation number 1 and check that the degree of y was not 1 throughout, so that was a Bernoulli differential equation, and with the help of these substitutions you have transformed equation number 1 to equation number 6, which is a linear differential equation in V. Now we will solve this differential equation with the usual method, that is, first we will find the integrating factor and then the general solution. So this is linear differential equation in V. Now we can compare it with the standard form of linear differential equation, that is dy by dx plus p dash y is equal to q dash. Here the dependent variable was y and in this equation number 6 the dependent variable is v. So comparing the values, we will get the value of p dash as minus 1 by x and q dash as minus log x by x. So since this is a linear differential equation, we can solve it with the help of the usual method. And the usual method is, first you have to find the integrating factor and then the general solution. So the formula for integrating factor is E integral p dash dx. Substitute the value of p dash, that is minus 1 by x dx, and integration of 1 by x is e raised to the power minus log x. Then by the property of log, this can be written as log x raised to the power minus 1. Again by the property of log, we will get the value as x raised to the power minus 1, or you can write it as 1 by x. So here we have used two properties of log. The first one is n log m is equal to log m raised to the power n. This we have used over here. Minus log x can be written as log x raised to the power minus 1 with the help of this property. And the second property is e raised to the power log x is nothing but x. So that property we have used it here. E raised to the power log x inverse is nothing but x inverse itself. So now we have calculated the value of integrating factor. Last step is to write the general solution of equation number 6. So that is given by v into integrating factor. Why we are writing v over here? Because from equation 6 we can have a view that the dependent variable used here is v. So the formula will be v into integrating factor is equal to whole integration q dash into integrating factor dx plus c. C is the constant of integration. So now we will substitute the value of integrating factor and integrate. So v into integrating factor is 1 by x, that is equal to q dash is minus of log x upon x multiplied by, again we have to write integrating factor dx plus c. So v by x is equal to minus log x upon x square dx plus c. Now you can see that we have integration of product of two functions. So for this we can use integration by parts. That means first we will have to select the first and the second function with the help of Eilert rule. So here in Eilert rule, I stands for inverse functions, L stands for logarithmic functions, A stands for algebraic function, T stands for trigonometric, and E stands for exponential function. So you can have a look at this integral. Here we have product of two functions, and out of this log x can be written as the first function, whereas 1 by x square can be written as the second function. So here the first function is log x, whereas the second function is 1 upon x square, not x square, it is 1 by x square. So then we will use the formula for integration by parts for the right hand side of this equation. The left hand side will remain as it is. So we have v by x written as it is, and integration of first and second function by parts is given by first function as it is, integration of second minus whole integration differentiation of first function into integration of second function with respect to x. So this is the formula, and we have already discussed what is first and what is second. So first function is log x, second function is 1 by x square. So we will substitute the value in the right hand side. Here we will have v by x is equal to, we have a negative sign over here, minus of, using the formula, first function is log x, multiplied by integration of second. So integration of second is 1 by x square dx, minus of whole integration differentiation of first, that is log x, multiplied by integration of second is 1 by x square, and we have a constant of integration c. So as you know, the power rule for integration is given by the formula x raised to the power n dx is equal to x raised to the power n plus 1 upon n plus 1. We are going to use this formula over here, and there, and also differentiation of log x is 1 by x. So, we are going to use these two formulas. So, left hand side will remain as it is, v by x is equal to, we are having a negative sign, minus of log x, integration with the help of this formula will give us minus 1 upon x, minus of whole integration, differentiation of log x is this 1 by x, multiplication of integration of 1 upon x square with the help of power rule is given by minus 1 by x plus c dx plus c. So, we have to integrate it once again, and v by x is equal to minus of log x upon x, minus of this minus and minus will become plus, integration of 1 upon x square dx plus c. So, what you can do, you can again multiply the negative sign with the square bracket, and the left hand side will remain as it is, v by x is equal to, as you can see you have a negative sign over here, minus and minus will become plus, log x by x, this minus and plus will become minus, and integration of 1 upon x square with the help of power rule will be written as minus 1 by x, and then we have a constant of integration c plus c. So, v by x is equal to log x upon x plus 1 by x plus c. Last step is to replace this v. So, as v is 1 upon y, we will replace this v. So, we have 1 upon y into 1 upon x is equal to log x upon x plus 1 by x plus c. So, this is the final answer for the differential equation.